What if you flew your spaceship straight ahead, past every planet, every star, every galaxy, and just kept going? Would you ever hit the edge of the universe? Or would you travel forever into endless darkness? This simple question, does space end, is one of the greatest mysteries of all time. And if you want the answer to that question, watch this video till the end and subscribe to the channel. Let's begin. When we ask, does space end? We're really trying to define what that question even means. Space isn't like a room with 4 walls or a map with a border marked in red. When scientists and philosophers talk about the end of space, they're asking whether the universe has a physical boundary, a place where everything simply stops, or whether it stretches on forever without limit. In everyday life, everything we experience has edges. A road ends, a sky meets the horizon, a coastline stops at the sea. But when it comes to the universe, those everyday rules may not apply. To end, space would need to have some kind of outer boundary, a cosmic edge beyond which there's simply nothing. No galaxies, no light, not even the fabric of space itself. But if there's an edge, what lies beyond it? Does nothing even make sense in a cosmic context? That's where things get tricky, because space itself is what defines where things exist. Without space, there's no beyond to talk about. So when we ask if space ends, we're really asking, is the universe finite, like a sphere or a loop that eventually curves back on itself, or infinite, stretching endlessly in all directions? Scientists have spent decades trying to answer this question, not by looking for a wall in the sky, but by studying the structure, shape, and expansion of the cosmos itself. And to understand where the limits of space might lie, we first have to understand the limits of what we can see. When we talk about the universe, there's a crucial distinction between everything that exists and everything we can see. What we can see, what our telescopes, satellites, and instruments can detect, is known as the observable universe. It's the portion of the cosmos whose light has had enough time to reach us since the beginning of the universe, about 13.8 billion years ago. Because light takes time to travel, looking out into space is also looking back in time. The farther we look, the older the light we're seeing. Some of the faintest light captured by our most sensitive telescopes began its journey toward us before Earth even existed. Now, you might assume that since the universe is about 13.8 billion years old, the observable universe should have a radius of 13.8 billion light-years. But it's much larger than that, about 46 billion light-years in every direction. The reason lies in the fact that space itself has been expanding since the Big Bang. While that ancient light was making its long journey to us, the very fabric of space was stretching, carrying distant galaxies even farther away. So, by the time that light finally reached Earth, the sources that emitted it were no longer 13.8 billion light-years away. They're now roughly 46 billion light-years distant. This gives the observable universe a diameter of around 93 billion light-years. To visualize this, imagine a massive cosmic bubble centered on Earth, expanding 46 billion light-years in every direction. Everything inside that bubble, every galaxy, star, and particle of light that has reached us since the dawn of time, is part of our observable universe. But here's the important part. That doesn't mean it's the whole universe. It's just the region that's visible to us from our position in space and time. Beyond that 46 billion light-year boundary, there may be vastly more universe, possibly infinite in extent, that we simply can't observe because light from those regions hasn't had enough time to get here yet. This limitation doesn't mean there's an edge in any physical sense. There's no invisible wall or cosmic curtain marking the end of existence. It's more like standing in the middle of a vast foggy landscape. You can only see as far as the fog allows, but the land doesn't stop where your vision ends. The universe beyond our observable bubble continues, but we are permanently cut off from it by the limits of light and time. This invisible frontier is known as our cosmic horizon, the ultimate boundary of observation. Every observer, no matter where they are in the universe, has their own unique observable bubble. If there's a civilization in a distant galaxy, billions of light years away, their observable universe overlaps with ours in part, but also includes regions we can never see. In that sense, every point in the cosmos has its own window into reality, a sphere of visibility bounded by the speed of light and the age of the universe. The deeper truth is that no one, anywhere, can see the entire universe. The observable universe isn't a fixed region. It's a cosmic mirage shaped by time, light, and expansion. This concept radically shifts how we think about the cosmos. When we look up at the night sky, we're not seeing the universe as it is now. We're seeing it as it was. The Andromeda galaxy, for example, is about 2.5 million light-years away, meaning we see it as it appeared 2.5 million years ago. When we observe the light from galaxies near the cosmic horizon, we're seeing them as they looked over 13 billion years ago, when the first stars were just forming. We can never see these galaxies as they are today, because the light they're currently emitting will never reach us. The expansion of space is carrying them away faster than light can travel. This cosmic speed limit creates a paradoxical situation. Even though we can measure, map, and study billions of galaxies, what we're actually seeing is a time-lapsed mosaic of the universe's history, not a snapshot of its present state. It's as if we're watching the flickering shadows of an immense reality that continues far beyond our reach. And that brings us to an even deeper question. If our observable universe is just one small bubble in an unimaginably larger whole, then how much more lies beyond what we can ever see? Could there be regions of space so distant that they'll remain forever hidden from us, galaxies whose light will never, in all eternity, reach Earth? Current cosmology says yes. The universe, as far as we can tell, extends far beyond our observational limits. It might even be infinite, stretching endlessly in all directions. Or it could be finite, but so vast that we'll never perceive its boundaries. The observable universe, then, is not the edge of existence. It's simply the limit of our perception, defined by the finite speed of light and the finite age of the cosmos. It's a humbling reminder that human knowledge, for all its brilliance, is confined to a tiny fraction of reality. The universe doesn't end at the edge of what we can see. That's merely where our tools, our eyes, and our understanding reach their limits. Beyond that horizon, the great unknown stretches on, perhaps forever. And to understand why we can't see beyond it, we have to explore the reason light and information itself can only travel so far. That takes us to one of the most fundamental principles of the cosmos, the speed of light, and how it defines the limits of our observable universe. The reason our observable universe has a boundary isn't because the cosmos stops there. It's because of the finite speed of light. Light, fast as it is, doesn't travel infinitely fast. It moves at about 299,792 kilometers per second, or roughly 186,000 miles per second, in a vacuum. That's the universal speed limit for all information, energy, and matter. Nothing in the universe can go faster. And as it turns out, that limit shapes everything we know about the cosmos, including how far we can see, what we can understand, and why it sometimes feels like space has an edge. Think about it. When you look at the moon, you're not seeing it as it is right now. You're seeing it as it was 1.3 seconds ago, because that's how long it takes light to travel from the moon to Earth. The sunlight glinting off the moon's surface left the sun about 8 minutes earlier, meaning the light from our nearest star takes 8 minutes to reach us. In a very real sense, every time we look up at the sky, we're looking back in time. Every star you see is a relic of the past. Some of them may have burned out long ago, but their light is still racing toward us across the vastness of space. Now, scale that concept up to the entire universe. The oldest light we can detect comes from about 13.8 billion years ago, emitted just after the Big Bang. This light, called the cosmic microwave background, CMB, is like a fossil glow from the birth of the universe. It's the edge of what we can observe, not because the universe ends there, but because that's the farthest distance light has had time to travel since the universe began. The universe could be infinitely larger than that. But we'll never know, because light from those farther regions hasn't reached us, and never will. This creates what scientists call a cosmic horizon, the ultimate observational limit. It's the dividing line between the part of the universe we can see and the part we can't. It's not a wall, not a physical barrier, but a boundary set by the interplay of time, space, and light. Beyond that horizon lies the unobservable universe, regions of space forever hidden from us because their light will always be outpaced by the expansion of the cosmos itself. Here's why. Space isn't static. Since the Big Bang, it's been expanding, stretching the distances between galaxies. Early in the universe's history, light from distant galaxies could reach us, because space hadn't expanded much yet. But as the universe aged, that expansion accelerated, driven by what we now call dark energy. Because of this, many galaxies are being carried away from us faster than light, not because they're breaking the cosmic speed limit, but because the space between us and them is stretching. When that happens, the light they emit will never make it to us. Those galaxies fade from view, slipping beyond our horizon forever. So even though the universe is about 13.8 billion years old, the edge of what we can see isn't 13.8 billion light years away. It's roughly 46 billion light years. This is because while light has been traveling toward us, the universe has continued expanding. Imagine shining a flashlight in a rubber balloon while it's being inflated. The beam travels through the balloon surface, but as the balloon expands, the distance between you and the light's destination grows. The farther the light travels, the more the balloon stretches beneath it. The light never speeds up. Instead, the space it moves through just keeps getting bigger. That's essentially what's happening to light in our universe. Now, this cosmic horizon creates an illusion that the universe might have an edge. From our perspective, we see a spherical boundary, the limit of our view, beyond which there's only darkness. But that darkness isn't nothingness. It's simply light that hasn't reached us yet. If you could somehow stand far outside our observable universe, impossible as that is, you'd see a completely different horizon centered around you. Every point in space has its own cosmic horizon, determined by how far light has traveled to that point since the beginning of time. This idea has deep implications. It means that the universe might look finite from where we are, but that's only an illusion caused by the limits of light and time. The cosmos may extend infinitely in every direction, or it may loop back on itself in a way that we can't yet perceive. Either way, our edge of the universe isn't a true edge. It's the farthest reach of the universe's oldest light. Beyond it, space may go on forever. The speed of light doesn't just define our visual horizon, it defines the boundary of human knowledge itself. Everything we know about the universe, every image from the Hubble or James Webb Space Telescope, every cosmic map, every bit of scientific data, is confined within this sphere of light. Outside it lies a realm we can theorize about but never observe, a part of reality forever beyond our grasp. This limitation is both humbling and awe-inspiring. It reminds us that the universe doesn't care about the boundaries of human perception. What we see is only a fraction of what exists. The cosmic horizon marks the line between the known and the unknowable, a shimmering boundary that expands with time but always hides more than it reveals. Yet, even with this limit, humanity has managed to uncover astonishing truths about what lies within that horizon. We've measured the structure of galaxies, mapped the afterglow of the Big Bang, and traced the motion of matter across billions of years. Still, one question lingers. If our view of the universe is limited, how can we possibly know what lies beyond it? To approach that mystery, we need to step back and think bigger, not just about what we can see, but about the universe as a whole, visible and invisible alike. And that brings us to the next step in our cosmic journey, understanding what might exist beyond our horizon, in the parts of the universe that remain forever hidden from view. When we peer out into the night sky, even with the most powerful telescopes ever built, we're only seeing a fraction, a breathtakingly small fragment, of what truly exists. Everything that lies within our cosmic horizon, that bubble of space about 46 billion light-years in radius, represents the totality of the observable universe. But here's the staggering truth. Beyond that glowing edge of visibility, there may lie vast stretches of cosmos we can never see, measure, or even imagine. The light from those distant regions will never reach us, not because it's too faint, but because it's forever cut off by the relentless expansion of space itself. Yet, just because we can't see those regions doesn't mean they're not there. In fact, most cosmologists believe that what we observe is just a tiny patch of a far larger, possibly infinite universe. The part of space we can detect is like a small spotlight illuminating a single ripple on an endless ocean. Beyond the reach of our light and instruments, space may continue endlessly, filled with galaxies, stars, and matter that follow the same laws of physics as the parts we can observe. These unseen regions might stretch forever, or they might wrap around in a vast, curved geometry that brings them back toward us in ways we can't yet perceive. The truth could be more extraordinary than anything our instruments can confirm. This realization is rooted in both mathematics and physics. The equations of general relativity, the framework Einstein gave us to describe space, time, and gravity, don't set a specific size for the universe. Instead, they describe how space behaves, how it bends, stretches, and evolves. When scientists plug our best data into these equations, measurements of the cosmic microwave background, galaxy distributions, and large-scale structures, they find no evidence of an edge, border, or boundary to the cosmos. The geometry appears flat on the largest scales, meaning parallel lines never meet, and the universe could, theoretically, extend forever. But this leads to a strange thought. If the universe really is infinite, then everything that could happen might happen, an infinite number of times. There could be other galaxies identical to the Milky Way, other solar systems just like ours, even other versions of you and me, scattered unimaginably far apart across an endless expanse. It's not science fiction. It's a direct consequence of infinity itself. Still, while the idea is mind-expanding, we can't confirm it, because we can't observe beyond our cosmic horizon. That horizon is the ultimate wall of information, the farthest we can ever look, no matter how advanced our technology becomes. To grasp the scale of what lies beyond, think of the observable universe as a small island floating in a boundless ocean. From our position on the island's shore, we can only see to the horizon, the point where sky meets sea. We know intuitively that the ocean doesn't stop there. It stretches far beyond our sight. Similarly, the universe doesn't end at 46 billion light-years. It just disappears from view. And the farther we peer into the darkness, the more we realize how much we'll never see. The cosmos, in its true extent, may be effectively infinite. Some scientists speculate that beyond our observable limits, the universe could have regions that look utterly different from ours. Maybe the laws of physics vary slightly, or matter is arranged in unfamiliar ways. It's even possible that enormous cosmic structures, clusters of galaxies beyond anything we've mapped, exist out there, influencing our own universe subtly through gravity. But we'll never detect them directly. Their signals are trapped beyond the cosmic event horizon, stretched into oblivion by the expansion of space. Even more astonishing is that the expansion of the universe itself means that the observable portion of reality is shrinking, in a sense. As space expands faster and faster, driven by dark energy, more galaxies are being carried away beyond our view every second. In the far future, tens of billions of years from now, distant galaxies will vanish completely from sight. If any civilizations exist then, their night sky will look almost empty. They'll never know that a vast universe once surrounded them. The cosmos will appear to end just beyond their local group of galaxies. To them, it will seem finite, even though we know it's not. That's how deeply the speed of light and cosmic expansion shape our understanding of existence. It's humbling to realize that we live at a unique moment in cosmic history, a time when the universe is still transparent enough and light has traveled long enough for us to see the cosmic web in all its glory. We can still glimpse the afterglow of the Big Bang, trace the filaments of galaxies across billions of light years, and map the vast structures of space before they fade into invisibility. Future civilizations might never have that privilege. We exist in a fleeting window of cosmic time when the universe reveals its scale. And even in that moment, we see only a sliver of what's really out there. So when people ask, what lies beyond the observable universe? The most honest answer is this: we don't know, and perhaps we never will. The unobservable universe remains forever beyond the reach of light, of instruments, and of knowledge itself. Yet its existence feels inevitable, supported by the mathematics of cosmology and the consistency of physical laws. Just because we can't observe it doesn't mean it's not real. The universe is almost certainly far bigger than our minds can comprehend, and perhaps infinite in its expanse. And that brings us to a deeper question. If the universe truly extends beyond what we can see, then what is its shape? Is it flat, stretching endlessly like an infinite plane? Is it curved, wrapping around itself like a cosmic sphere? Or is it something stranger still, something that defies every metaphor our human minds can create? When we think about the universe, it's natural to picture it as an enormous, endless space, something stretching infinitely in all directions. But in cosmology, scientists go deeper than that. They don't just ask how big the universe is, they ask what shape it has. This might sound abstract at first, but the shape of the universe, its overall geometry, is one of the most important clues to understanding whether space ends, loops back on itself, or extends forever. In simple terms, there are three main possibilities for the shape of the universe: flat, open, or closed. These aren't about physical surfaces, like the edge of a planet. They're about how space itself is curved on the largest scales. To make sense of it, imagine for a moment that you're an explorer living on a two-dimensional world, a world where you can move forward, backward, left or right, but not up or down. You have no sense of height. Your reality is completely flat, like a sheet of paper. Now, your world could take one of three forms: flat like that sheet, curved like the surface of a balloon, or saddle-shaped like a horse's saddle. Each of these shapes represents one of the possible geometries of the universe. In a flat universe, parallel lines never meet. If you drew two straight lines side by side on that paper world, they would continue forever without ever touching. Angles in a triangle would add up to exactly 180 degrees, and space would feel normal in the way we intuitively understand it. A flat universe can extend infinitely, never looping back on itself. It could go on forever in every direction, without end or boundary. Now imagine your 2D world isn't on a flat sheet, but wrapped around the surface of a balloon. If you started walking in one direction, you'd eventually come back to where you started, never encountering an edge. That's a closed universe. In this kind of cosmos, space is curved inward, like the surface of a sphere. Parallel lines that start out side by side will eventually meet, just as two lines of longitude meet at the poles of Earth. This universe is finite in size, but has no edges. It's limited, but unbounded. You could travel forever and never fall off. To the inhabitants inside it, it might feel infinite, even though it loops back on itself. The third possibility is an open universe, which has negative curvature. Imagine a saddle that curves downward in one direction and upward in another. In this kind of geometry, parallel lines move farther and farther apart as they extend. Triangles drawn on such a surface would have angles adding up to less than 180 degrees. A universe with negative curvature doesn't loop back on itself. Instead, it expands outward infinitely, with space curving away endlessly. It's infinite, but it has a shape that affects how light and matter behave across cosmic distances. These shapes, flat, closed, or open, aren't just thought experiments. They have very real implications for how the universe behaves. The geometry determines the fate of everything, how galaxies cluster, how light bends as it travels, and even whether the cosmos will expand forever or eventually collapse back on itself. Early in the 20th century, scientists like Albert Einstein and Alexander Friedman used the equations of general relativity to show that the universe's shape is linked directly to its density, specifically how much matter and energy it contains. If there's a lot of matter, gravity will pull space inward, creating a closed universe. If there's too little, space will curve outward, forming an open one. If the density is just right, balanced perfectly, then space will be flat. This idea led cosmologists to a powerful prediction. By measuring the density of matter and energy in the universe, and observing how light travels across immense distances, we can infer its overall geometry. That's why scientists look so closely at the cosmic microwave background, the faint afterglow of the Big Bang. Tiny fluctuations in that ancient light encode the shape of space itself. When scientists measure those patterns, they can tell whether light is being stretched, bent, or distorted by the curvature of the cosmos. The analogy of a balloon helps us visualize it, but it's important to remember that when cosmologists say the universe might be curved, they don't mean it's curving in something else. The universe isn't expanding into an empty void or bending through some higher dimensional space, at least not in the ordinary sense. The curvature exists within the universe itself. Just as the surface of a balloon is curved but has no edge from the perspective of a two-dimensional being, our three-dimensional universe could be curved without having an outside at all. The geometry defines the shape of space, not its surroundings. Imagine living in a closed universe for a moment. You could, in theory, take a spaceship and fly straight ahead forever. After billions or trillions of years, if you traveled fast enough and space didn't expand too much, you might find yourself returning to your starting point, from the opposite direction. It's like circumnavigating the globe, but in 3 dimensions instead of 2. On the other hand, if the universe were open or flat, you could keep traveling forever and never return. just endless stars and galaxies fading into the infinite distance. So which one is our universe? That's the question cosmologists have been testing for decades. The answer seems to point strongly toward flatness, a universe where, on the largest scales we can measure, space doesn't curve inward or outward. But that flatness doesn't mean simple or boring. It could still be infinite, or it could loop in ways we haven't yet detected. And that brings us to the next step in understanding what flat really means in cosmology, why it's such a big deal that space appears flat, and how that might reveal whether the universe truly goes on forever or hides subtle curves too vast for us to detect. When scientists say the universe is flat, they're not talking about it being flat like a pancake floating in space. They mean that, on the largest possible scales, billions upon billions of light years, the geometry of the universe follows the rules of Euclidean space, the geometry most of us learned in school. In this kind of space, parallel lines never meet. The angles of a triangle always add up to 180 degrees, and light travels in straight paths rather than curving dramatically across cosmic distances. The universe being flat means that, as far as we can tell, space doesn't bend inward like a sphere or outward like a saddle. It simply extends straight and steady, without measurable curvature. But how do we know that? How can we measure something as abstract as the curvature of space itself? The answer lies in the oldest light in the universe, the cosmic microwave background, CMB. This faint afterglow, discovered in 1965 by Arno Penzias and Robert Wilson, is radiation left over from the Big Bang. It fills the entire sky, a relic of the moment when the universe was only about 380,000 years old. When we map the CMB with incredible precision, using telescopes like NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck satellite, we can detect tiny fluctuations, minute temperature differences, that reveal the large-scale shape of the cosmos. Here's how it works. Imagine the early universe as a hot, dense soup of particles and light. Tiny ripples, regions slightly denser than others, formed as gravity pulled matter together while radiation pushed it apart. These ripples left behind a distinctive pattern in the CMB, like sound waves frozen in time. By measuring the apparent size of those patterns in the sky, scientists can determine whether the universe bends space to make those features appear larger or smaller than they actually are. If the universe were closed, curved inward like a sphere, light from those ripples would bend toward itself, making the patterns appear larger. If the universe were open, curved outward like a saddle, light would spread apart, making the patterns look smaller. But what scientists found was astonishing. The patterns in the CMB appear exactly the size they should in a flat universe. In 2013, the Planck mission provided the most precise measurement of this curvature yet. The results showed that the universe is flat to within an error margin of just 0.4%. In cosmic terms, that's astonishingly flat. So flat that, if the universe were the size of the observable cosmos, its curvature would be undetectable across distances of hundreds of billions of light years. If you scaled it down, it would be like looking at the surface of Earth and seeing no curvature even after traveling around it millions of times. On the largest scales we can probe, space behaves as if it extends endlessly in every direction. This flatness implies something profound. In general relativity, the geometry of the universe is determined by its density of matter and energy. If the total density equals a critical value, precisely balanced between collapse and endless expansion, the universe will be flat. Measurements of the CMB, galaxy clustering, and the distribution of dark matter and dark energy all point to this exact balance. That's not just a coincidence. It's a deep clue about the early universe. Cosmologists believe that an event called cosmic inflation, a brief, unimaginably rapid expansion in the first fraction of a second after the Big Bang, stretched the fabric of space so violently that any initial curvature was smoothed out, like an inflated balloon appearing flatter the larger it grows. Inflation would explain why the universe today looks so incredibly flat, even though small irregularities existed in its infancy. To appreciate what this means, think of standing in the middle of an enormous plain, so vast that no matter how far you walk, the ground always looks level beneath your feet. You can't see any curvature because the landscape is too immense. That's the situation we're in. Our instruments can probe space across tens of billions of light years, yet we find no detectable curvature. If there is curvature, it must be spread across scales far larger than we can ever observe. The universe might still be gently curved, looping subtly upon itself in a way that no telescope could ever reveal. But to us, it appears flat as far as our cosmic eyes can see. Flatness also carries philosophical weight. If the universe truly is flat and infinite, then there's no edge, no boundary, no outside. Every direction stretches endlessly, filled with countless galaxies, perhaps infinitely many, spread throughout space. Every patch of sky you look at could contain endless layers of structure, extending far beyond the limits of light. In an infinite, flat universe, there's no center either. Every point in space is as valid as any other, which means the Earth, our Sun, our galaxy, none of them occupy a special position. We exist in a universe that doesn't revolve around us, a cosmos without boundaries or favored places. But this conclusion comes with a caveat. Our observations only extend so far. The universe appears flat within the observable region, but that's just one cosmic patch in an unfathomably larger whole. It's possible that, on scales beyond what we can measure, the universe bends subtly, like a globe so large its curvature can't be seen from ground level. In that case, what we call flat might simply be our limited perspective, a local truth, not an ultimate one. Still, the evidence we have paints a stunning picture. A flat universe doesn't just suggest endless space. It also implies that the cosmos might continue expanding forever, never collapsing back into a big crunch. Galaxies will drift farther apart, stars will fade, and over unimaginable stretches of time, the universe will grow cold and dark. That's the destiny of a flat, ever-expanding cosmos. And yet, this flatness doesn't close the case. Even if our universe seems perfectly balanced, there's always the possibility that it's only nearly flat, that a faint curvature hides beyond the horizon, too subtle for us to detect. If so, that slight curve could tell us something extraordinary about the universe's true size, shape, and ultimate fate. So before we declare the cosmos infinite and flat forever, we must consider the possibility that it's not perfectly flat at all, but just curved so gently that our tiny window into it can't see the bend. When scientists say the universe is flat, it's important to remember that this flatness is a measurement, not an absolute truth carved into cosmic stone. Our instruments, powerful as they are, only allow us to observe a small portion of the entire universe, and within that region, space looks perfectly flat. But what if that's just an illusion created by our limited vantage point? What if, on scales far larger than we can ever see, the universe is actually slightly curved, so gently, so imperceptibly, that we'll never notice it? To understand how this could be possible, picture standing on the surface of the Earth. To your eyes, the ground looks perfectly flat in every direction. You can walk for miles, or even hundreds of miles, and it still looks flat. Yet, we know the Earth is round. Its curvature is real, but it's so gradual that you can only perceive it from far above, from the vantage point of space. Now imagine scaling that concept up to the entire universe. The flatness we see, could simply mean that the patch of cosmos we observe is too small compared to the whole to reveal the gentle curve that exists on a much grander scale. If the universe were curved like the surface of a vast sphere, what cosmologists call a closed universe, then, in theory, if you traveled far enough in one direction, you could eventually return to your starting point. This idea feels almost impossible to grasp because it challenges our most basic intuitions about space. But in a curved universe, straight lines, or rather, what physicists call geodesics, eventually loop back around, just like how planes flying straight across Earth's surface eventually return to where they began. If our universe were curved in this way, we'd all be living inside a kind of cosmic bubble, finite in size but without any edges. On the other hand, if the universe had negative curvature, like the surface of a saddle, it would curve outward instead of inward. In that case, space would expand infinitely, but the geometry would still be subtly warped. Two parallel beams of light, instead of staying perfectly parallel, would gradually diverge as they crossed the cosmos. From a local perspective, this would be virtually impossible to detect, but across unimaginable distances, that tiny divergence could alter the shape and fate of the universe. The difficulty is that the observable universe, the sphere of space we can measure, is only a tiny fraction of the whole. If the entire cosmos were the size of Earth, then our observable universe might be no larger than a single room. Within that room, the floor would seem perfectly flat. You'd see no sign of curvature whatsoever, even though the surface beneath you is part of a massive sphere. That's essentially our situation. Our telescopes can probe roughly 46 billion light-years in any direction. But if the true curvature of space only becomes apparent over scales hundreds or thousands of times larger than that, we'd never know. The data we have so far, primarily from the Planck satellite and other cosmic surveys, supports a universe that is very close to flat. But very close is not the same as exactly. The measurements tell us that if there is any curvature at all, it's so small that the universe's radius of curvature must be at least hundreds of times larger than the observable cosmos. In simple terms, the universe could be a sphere so vast that even if we traveled billions of light-years in one direction, space would still look perfectly straight beneath our cosmic feet. It's also possible that the universe's curvature isn't uniform everywhere. Some theoretical models propose that space could be locally flat, appearing flat in small regions like ours, but curved differently in distant parts of the cosmos. If inflation stretched space to near flatness, as most cosmologists believe, tiny variations could remain, ripples in the overall shape of the universe, too subtle to detect from within our small observational bubble. These ripples could one day leave traces in the cosmic microwave background, or in the way light from ancient galaxies bends and distorts as it travels through space. Another fascinating idea is that even if the universe is curved, we might still never perceive that curvature directly, because cosmic expansion constantly pushes distant regions farther away. It's like being trapped in a foggy valley on a planet so large that you can never climb high enough to see its curve. The observable horizon, the farthest point we can see, acts as a kind of built-in limit. Even if the universe loops back on itself, the light from the far side might never have time to complete the journey and return to us. We'd live our entire cosmic lives believing space to be infinite, when in truth it might only be vast and circular. There's also a poetic irony in this. Our universe could, right now, be gently curving back on itself, and yet no being within it, no telescope, no civilization, could ever detect it. The limits of light and time conspire to hide the true shape of reality from us. In this sense, we may be like fish in a perfectly round bowl, swimming in endless circles and mistaking the curve of the glass for infinity. Still, science continues to test the limits of precision. Future missions, like NASA's proposed CMBS-4 observatory or the European Space Agency's Euclid mission, aim to refine our measurements of cosmic curvature even further. If they find the tiniest hint of curvature, it would revolutionize our understanding of the cosmos. It would mean the universe is not infinite after all, but rather a closed, self-contained system, perhaps looping back on itself in dimensions beyond our comprehension. If they confirm flatness even more precisely, that would suggest we live in a truly infinite expanse, one that stretches endlessly beyond all horizons. But for now, the evidence leans toward a universe that's astonishingly, almost eerily flat. If there is curvature, it's hidden so well that our observable universe might as well be a single, imperceptible patch on a cosmic balloon too large to ever grasp. Whether we live in a perfectly flat infinity or a gently curved hole remains one of the most profound mysteries in all of cosmology. And yet, the shape of space isn't the only thing changing. The universe itself is expanding. The distances between galaxies aren't fixed, they're stretching over time. To understand the full picture, we must look not only at the shape of space, but at how it grows. Because the expansion of the universe is what gives rise to one of the most beautiful and misunderstood truths in cosmology. When we talk about the expansion of the universe, it's easy to imagine galaxies speeding through space like fireworks racing away from an explosion. That image, though vivid, is fundamentally misleading. The galaxies themselves aren't flying through a pre-existing space. Rather, space itself is expanding. The very fabric of the cosmos is stretching, carrying galaxies with it, the way raisins move apart in a loaf of rising bread. The galaxies aren't moving through the dough. It's the dough that's expanding between them. This concept is one of the most mind-bending discoveries in all of science. It began with Edwin Hubble's observations in the 1920s, when he discovered that distant galaxies were receding from us, and that the farther away they were, the faster they seemed to be moving. This relationship, now called Hubble's law, showed that the universe isn't static. It's dynamic, evolving, and expanding. Every galaxy is moving away from every other galaxy, not because they're propelling themselves, but because the space between them is growing. Imagine you're sitting in a giant balloon and tiny dots are painted all over its surface to represent galaxies. As the balloon inflates, each dot moves away from the others. From your perspective on one of those dots, it looks like everything around you is receding, and the farther a dot is, the faster it seems to move. There's no single center to this expansion. Every point in space is getting farther from every other point. The same thing is happening in our universe. From Earth's vantage point, it appears that all galaxies are moving away from us. But if you were standing in any other galaxy, you'd see the same thing. The expansion is everywhere, uniform and relentless. But what's even more astonishing is that this expansion isn't just continuing, it's accelerating. In the late 1990s, two teams of astronomers studying distant supernovae discovered something unexpected. The rate at which galaxies are receding isn't slowing down due to gravity, as everyone had assumed. Instead, it's speeding up. Something mysterious, dubbed dark energy, is driving this acceleration. Dark energy appears to make up about 68% of the total energy of the universe, acting as a kind of repulsive force that counteracts gravity on the largest scales. Its nature is still one of the greatest enigmas in physics, but its effect is unmistakable. The expansion of space is increasing, and the galaxies are drifting apart faster than ever before. The consequences of this accelerating expansion are profound. As space stretches, the light traveling across it also stretches, a phenomenon known as cosmological redshift. The wavelength of light elongates, shifting toward the red end of the spectrum, and as it continues to stretch, it eventually moves beyond visible light, beyond infrared, and finally into wavelengths we can no longer detect. This means that as the universe expands, distant galaxies are literally fading from our view, not because they've dimmed or vanished, but because their light has been stretched into invisibility. There's a haunting beauty in this. Every second, space expands a little more, and with each passing moment, more galaxies cross a threshold called the cosmic event horizon, a point beyond which their light will never reach us, no matter how long we wait. The expansion of space is carrying them away faster than light can travel through it. To be clear, these galaxies aren't breaking the speed of light in the traditional sense. Einstein's cosmic speed limit still holds. It's not the galaxies themselves that are moving faster than light, but rather the space between us and them that's stretching so rapidly that their light can't keep up. In time, this means that the observable universe is shrinking in terms of what we can see, even though the total universe continues to grow. Billions of years from now, galaxies outside our local group, the small cluster containing the Milky Way, Andromeda, and a few dozen smaller galaxies, will fade from view altogether. They'll slip beyond the cosmic horizon, their light stretched and dimmed until it's lost forever. If intelligent life exists in the far future, billions of years from now, they'll look out into a dark, empty sky. They'll see only their own galaxy, perhaps a few faint companions, floating in an otherwise black void. The cosmic story written in the light of distant galaxies, the evidence that the universe is expanding, will be gone. To them, it will appear as if the universe has always been still and unchanging. Right now, we exist at a special moment in cosmic history, a time when the light from distant galaxies still reaches us, when we can still see the large-scale structure of the cosmos, and when we can trace its history back to the Big Bang itself. We're lucky in a cosmic sense, living at a time when the universe is transparent enough to show us its grandeur, yet not so far in the future that most of it has disappeared from view. In the vast timeline of cosmic evolution, this is a brief window of visibility, a golden moment when the universe reveals its secrets before fading into darkness once more. The expansion of space also reshapes how we think about distance. When astronomers say a galaxy is 10 billion light-years away, that doesn't mean its light has been traveling through a fixed space for 10 billion years. During that time, the universe has expanded enormously. The galaxy that emitted that light is now much farther away, perhaps more than 30 billion light-years distant. In an expanding universe, distance itself is not a simple static concept. Space is dynamic, ever-changing, and the geometry of that expansion affects everything from how we measure time to how we understand the fate of the cosmos. And yet, this expansion poses an even deeper question. If space itself is expanding, what is it expanding into? Is there some vast void outside the universe that's stretching to make room for more space? The answer, as strange as it sounds, is no. Space doesn't expand into anything. There is no outside of the universe. The expansion happens everywhere within the universe simultaneously. The distances between galaxies grow, but there's no boundary, no external space into which it's expanding. This is one of the most difficult but profound ideas in cosmology, and understanding it changes how we think about the very fabric of reality. Because to truly grasp what cosmic expansion means, we must abandon the notion of an edge. There's no outer rim of the universe, no boundary line separating something from nothing. Space itself grows, but it grows within itself. It's not expanding into a larger emptiness. Instead, new space is continuously coming into existence everywhere, stretching the universe from within, like the surface of a balloon inflating, but without an external space surrounding it. And that idea, that space is expanding but not into anything, leads naturally to one of the most fascinating and counterintuitive concepts in modern cosmology, that the universe might be finite but unbounded, limited in size yet without any edge at all. It's one of the hardest ideas for the human mind to accept. The universe is expanding but not into anything. When we hear the word expansion, we instinctively imagine a balloon swelling into empty air or an explosion radiating outward through space. But in the case of the universe, that's not what's happening at all. The expansion of the universe doesn't involve space moving into a pre-existing void. It's space itself that's growing, stretching, and creating new distances between galaxies everywhere at once. There is no outside for it to expand into, because space and time together are the universe. The universe isn't expanding into space, it's expanding as space. To grasp this, it helps to return to one of cosmology's favorite analogies, the surface of a balloon. Imagine that the entire universe is painted on the surface of the balloon, not inside it, not outside it, just on the two-dimensional skin. Galaxies are tiny dots scattered across that surface. As the balloon inflates, the dots move farther apart, but not because they're crawling along the rubber. Rather, the rubber itself is stretching, increasing the distance between every point. From the perspective of the dots, the universe, the balloon's surface, is expanding, yet there's no edge anywhere on that surface. You can travel endlessly in any direction and never fall off. Now, in reality, our universe isn't two-dimensional like the balloon's surface. It's three-dimensional, and that's where the analogy begins to strain. But the principle remains the same. As the universe expands, it's not pushing into an outer void. The outside doesn't exist within the framework of our universe. All of space, time, energy, and matter exist within this expanding fabric. The question, what is the universe expanding into, is a natural one, but it assumes that space exists within something larger, a container, a backdrop, an external environment. That's how we experience expansion in our everyday lives. A gas expands into air, water spreads into an empty cup, a balloon grows into the surrounding room. But cosmology operates on a different level. The universe doesn't exist in anything, it is everything. The concept of an outside of the universe is meaningless because space itself, the very notion of where, only exists inside the universe. Beyond it, there is no space, no time, no dimension for the universe to grow into. There's simply nothing, not even the kind of nothing we normally imagine, because even emptiness is still a form of space. When scientists talk about the expansion of the universe, they're describing how the metric of space changes. That is, how the scale of distances between objects increases over time. This means that if you pick any two galaxies that aren't gravitationally bound, like the Milky Way and Andromeda, which are close enough to be pulled together, the space between them will grow as the universe expands. But this happens everywhere, not from a single central point. There's no center of the universe where expansion began, and no outer rim where it's headed. From any galaxy, anywhere, the rest of the universe appears to be moving away. Every observer, no matter where they are, sees themselves as the center of the cosmic expansion. Not because they are special, but because expansion occurs uniformly in all directions. To visualize this, imagine an infinite loaf of raisin bread rising in the oven. As it bakes, the dough expands uniformly, carrying the raisins with it. From the point of view of any single raisin, every other raisin seems to be moving away, and the farther a raisin is, the faster it appears to recede. But there's no edge of dough pushing into the oven's air. The dough itself is expanding, and there's no need for an outside into which it grows. The same is true of our universe. Galaxies aren't hurtling through pre-existing space. They're embedded in a fabric that's stretching everywhere at once. This concept also means that the Big Bang wasn't an explosion that happened at a single point in space and flung matter outward into emptiness. The Big Bang happened everywhere at once. It wasn't the expansion of matter into space, but the expansion of space itself, filled with matter and energy. Every point in the universe today was once compressed together in that early hot, dense state. So if you were to rewind the expansion, you wouldn't see galaxies converging toward a single location. Instead, you'd see the entire fabric of space contracting uniformly until everything was squeezed into a single, extremely dense and hot condition, the primordial universe itself. Then, with the onset of expansion, every point in space began moving away from every other point, not through space, but as part of the expansion of space. It's also crucial to understand that the universe doesn't have a physical boundary or a center in the traditional sense. The center of the universe exists everywhere because expansion occurs uniformly everywhere. Similarly, there's no outer shell or frontier that marks where the universe ends. Even as the distances between galaxies grow, no new territory is being occupied, and no edge is being pushed outward. Expansion doesn't mean invasion into a void. It's a change in the scale of the universe itself. The distances increase, the wavelengths of light stretch, and time itself flows differently as the cosmic fabric evolves. One way to think about this is in terms of geometry rather than motion. The universe doesn't expand into space, it expands within its own geometry. The equations of general relativity describe how this geometry evolves. When cosmologists say that the scale factor of the universe is increasing, they mean that the grid lines of space, the coordinate system that defines distances, are stretching apart. Nothing is moving through this grid. The grid itself is expanding. In a sense, the expansion of the universe is not about objects moving in space, but about the increase of space itself between those objects. This idea challenges the limits of language, because our everyday words like grow, expand, and move all imply a background, something into which growth or motion happens. But the universe has no such backdrop. It is self-contained, self-referential, and self-expanding. If you ask, where is the universe expanding into? The only possible answer is nowhere. Space is not expanding into something else. It's simply becoming more of itself. And that realization leads us toward one of the most elegant and fascinating possibilities in physics, the idea that the universe could be finite but unbounded. In other words, it could have a limited total volume, but no edge, no outer wall, no border to fall off. Just as the surface of a sphere is finite in area but has no edge, our universe could be the three-dimensional equivalent, a space that loops back on itself, endlessly connected, yet without limits. When Albert Einstein first developed his general theory of relativity in 1915, he didn't just rewrite the rules of gravity. He redefined space and time themselves. In his equations, space and time were not rigid, unchanging backdrops where the universe played out its events. They were dynamic, flexible, and responsive to energy and matter. Space could curve, twist, and expand. And from this new way of understanding the cosmos came one of the most elegant and mind-stretching possibilities in all of physics. The universe could be finite but unbounded, limited in size, yet without any edges or borders whatsoever. This idea seems contradictory at first glance. How can something be finite but have no edge? We're used to finite things having boundaries. A table ends where its wood stops. A planet ends where its surface meets space. But Einstein's insight was that geometry itself can define limits without requiring edges. He realized that the universe could be self-contained, curving back on itself in higher dimensions, the way the surface of a sphere encloses a finite area without any boundary lines. To picture this, Think about the surface of the Earth. It's a two-dimensional surface wrapped into a three-dimensional shape. If you start walking in a straight line on Earth, you never encounter an edge. You don't fall off into space. Instead, after enough time, you come back to where you started. The surface is finite. It has a measurable area, but it's also unbounded because you can move endlessly without ever hitting a wall. Now imagine extending that principle up by one dimension. Instead of a two-dimensional surface curving within a three-dimensional space, think of our three-dimensional universe curving within a higher dimensional structure. That's the essence of what Einstein meant by a finite but unbounded cosmos. In this kind of universe, space curves back on itself. If you could somehow travel far enough in one direction, assuming expansion didn't pull everything apart faster than you could move, you might eventually end up back where you started, just as a traveler on Earth returns to their point of departure after circling the globe. You wouldn't find an edge of the universe because there wouldn't be one to find. There'd be no cliff at the end of existence, no wall of space, no surrounding void waiting beyond. Space would simply loop back around on itself endlessly, forming a vast, self-contained continuum. Einstein's idea arose when he applied his equations to the entire cosmos for the first time. The equations of general relativity described how matter and energy curve space-time, and how that curvature determines the motion of matter in return, a self-consistent dance between geometry and gravity. When Einstein looked for a static solution, a universe that wasn't expanding or contracting, he found that his equations naturally predicted that space must be curved like the surface of a sphere if it contained enough matter. This led him to propose a closed universe, one that's finite in volume but has no edges, just as the Earth's surface is finite in area but has no end. Though we now know the universe is expanding, Einstein's concept of a finite yet edgeless cosmos remains one of the most profound insights in the history of science. It showed that space doesn't need to be infinite to have no boundaries. The universe could, in theory, have a total size, a total volume, yet still feel endless to any observer inside it. Every direction would lead you back toward yourself eventually, though the scale of such a journey would be so vast that no being or civilization could ever make it all the way around. The beauty of this idea lies in how it reconciles two seemingly opposite intuitions. The universe feels infinite because there's no edge, but it can still be finite in extent. It's like a cosmic trick of geometry, a universe that encloses itself completely, leaving no outside at all. There's no beyond, no larger space that contains it, because the universe doesn't need anything external to define it. It is, in a sense, all there is. A self-contained system with its own internal rules and shape. To help visualize this, cosmologists often use the analogy of a 2D creature living on the surface of a balloon. To that creature, its world has no edges. If it keeps walking in any direction, it will eventually circle back to its starting point. The creature might imagine that its universe is infinite because it can't perceive the balloon's curvature within a higher dimension. It's trapped in 2 dimensions and cannot conceive of the 3rd dimension that allows the surface to curve. In the same way, we 3-dimensional beings might live inside a space that curves in a higher dimension, but we cannot perceive that curvature directly. From our perspective, the universe would appear unbounded, infinite even, though it might be a vast but closed 3D hypersphere. Einstein's finite but unbounded model also carries deep philosophical meaning. It suggests a universe that is both self-contained and complete, one that needs no outside to exist. There's no edge where the laws of physics break down, no border where you could peer beyond existence. Everything that can exist exists within the fabric of space-time itself. This vision of the universe was revolutionary because it broke from all previous human conceptions of space. For thousands of years, people imagined the cosmos as a vast container filled with stars, bounded by some ultimate edge or boundary. Einstein's relativity showed that space isn't a container at all. It's a dynamic, flexible fabric that can curve upon itself and define its own limits. If the universe truly is finite but unbounded, then every direction we look in space eventually leads back to where we are, though the distances are so enormous that we'd never notice. Light itself could, in theory, circle the cosmos and return to its origin, meaning that the night sky might, in some unimaginable way, contain echoes of our own galaxy's light from ancient ages. Though we haven't detected such repetitions, scientists still consider the possibility through a field called cosmic topology, which explores how the shape and connectedness of space could produce such phenomena. The finite but unbounded model doesn't just resolve the "what's outside the universe" question. It transcends it. It tells us that the universe doesn't need an outside. It exists entirely on its own terms, defined by its internal geometry. The question, "what's beyond?" becomes meaningless because beyond implies space, and space itself only exists within the universe. And yet, even with this elegant picture of a curved, self-contained cosmos, our minds still struggle to fully grasp what it means to live in such a reality. So, to bring it closer to home, to something our imagination can truly feel, let's step back to a simpler, more tangible analogy, one that helps us feel what a finite but unbounded world might be like. To truly wrap your mind around what a finite but unbounded universe means, let's use a simpler analogy, one grounded in something we can actually imagine. Picture yourself walking across the surface of the Earth. You start at some point, say, on a quiet beach, and begin walking in a straight line. You keep going and going, through forests, across oceans, over mountains, past continents, and eventually, after a long journey, you find yourself right back where you started. You never once reached an edge. You never fell off. There was no cliff marking the end of the world. The surface of the Earth, though finite in area, has no boundary. That's exactly what finite but unbounded means. The Earth is not infinite. You can measure its circumference, map its continents, and calculate its surface area. But you can move across it forever without ever encountering a wall or a border. Its geometry wraps around itself. It's self-contained. From the perspective of someone walking on it, there's no direction that leads to an outside. Now imagine taking that concept and expanding it by one dimension. Instead of a two-dimensional surface curving into three-dimensional space, imagine a three-dimensional space curving into a higher dimension. That's the kind of space our universe could have. You could, in principle, travel straight ahead through space forever and, if the universe were closed and curved enough, eventually loop back to where you started, without ever crossing an edge or finding an end. You'd never hit a wall, and there'd be no sign saying, "Here the universe stops." You'd simply continue moving through space that curves back on itself, like an ant walking endlessly around the surface of a globe. To the ant, the world seems infinite. It can walk in any direction without end. It doesn't perceive the curvature of the surface because it's too small to see it. The horizon always looks straight. The ground beneath its feet feels flat. Yet the ant is actually moving along a curved, finite surface. We humans are in a similar situation. Our observable universe, the part we can see, might be just a small patch of a much larger cosmic surface. From our vantage point, space looks flat and infinite. But that could simply be because we can only see a tiny fraction of its total extent. If the universe is curved on a scale far beyond our cosmic horizon, we'd never notice the bend. It would appear perfectly flat to us, just as Earth's curvature seems invisible to someone standing on its surface. This analogy also helps explain why we can't talk meaningfully about what's outside the universe. When you're standing on the Earth, the word outside has no meaning unless you leave the surface entirely. But if you're confined to that two-dimensional surface, outside doesn't exist in your reality. You could walk east forever, circle the planet 1,000 times, and still never encounter a point where the Earth's surface stops. The same applies to our three-dimensional universe. We exist within the fabric of space itself, and there is no outside to travel to. Every direction you look in leads you deeper into the universe, not out of it. It's also worth noting that even if space is finite in this way, it's immense beyond comprehension. Just because the universe might loop back on itself doesn't mean you could actually circle it. The scale is so enormous that light, which has been traveling since the beginning of time, may not have had enough time to make a full circuit. So while it's theoretically possible that light, or even matter, could eventually return to its origin, in practice, the universe is expanding so quickly that such a loop may never be completed. Still, the geometry remains. A cosmos with no edges, no outside, no end. This two-dimensional analogy also gives us a way to understand how light behaves in such a universe. If you could send out a beam of light in a perfectly straight line across this curved space, it wouldn't go out into nothingness. It would follow the curvature of space itself. In a closed universe, that light could theoretically return from the opposite direction, like a message sent around the world arriving back at its starting point. Some cosmologists have even suggested that if the universe were small enough, we might see multiple images of the same galaxies in different parts of the sky, light looping around the cosmos and arriving here more than once. Though we haven't found such evidence yet, it remains a fascinating possibility, one that ties geometry, physics, and observation together in a single, elegant framework. The beauty of the finite but unbounded concept is how it breaks free from human intuition while still remaining logically and mathematically consistent. It shows that infinity and limitation can coexist, a universe that feels infinite but is actually self-contained. It also dissolves one of humanity's oldest questions: what's beyond the edge of the universe? The answer is simple but profound. There is no edge. Asking what's beyond the universe is like asking what's north of the North Pole. It's a question that only seems sensible until you realize that it doesn't apply to the geometry of reality. So as you imagine yourself walking endlessly across the surface of this cosmic sphere, you begin to understand what Einstein meant when he said the universe could be finite, but without borders. You can go on forever, and yet space itself is a closed loop, an endless horizon that always leads back to itself. But even as this model elegantly explains the idea of a self-contained cosmos, it's not necessarily the whole story. There are theories suggesting that our entire universe, finite or infinite, might be just one bubble among countless others, each with its own laws of physics, its own version of reality. This takes us from geometry into one of the most audacious and speculative frontiers of modern cosmology, the multiverse. Now that we've explored the possibility that our universe might be finite yet unbounded, a self-contained space curving back on itself, it's natural to wonder if even that is the whole story. What if our universe, vast and all-encompassing as it seems, is just one bubble floating in a far greater cosmic ocean? What if there are other universes beyond ours, realities with their own laws of physics, their own beginnings, and perhaps their own versions of life? This is the realm of one of the most mind-expanding and controversial ideas in modern science, the multiverse. The multiverse concept suggests that our universe might not be unique. Instead, it could be one of countless universes forming an enormous, possibly infinite collection of realities. Each of these universes, or Bubble universes, as some physicists call them, might have arisen from its own Big Bang, with its own space, time, and physical constants. Some could resemble ours closely, while others might be so different that their physics would be utterly alien, worlds with different forms of matter, forces, or even dimensions. But before diving too deep into that speculation, it's important to emphasize something crucial. The multiverse remains a theoretical idea. There's no direct evidence for it. It's not something we can observe with telescopes, measure with detectors, or confirm through cosmic surveys. It arises from extensions of established theories, especially from ideas in cosmic inflation, quantum mechanics, and string theory, that seem to naturally predict other universes, even though we have no way, at least yet, to test those predictions directly. One of the most prominent versions of the multiverse idea comes from the theory of eternal inflation. According to inflation theory, in the first fraction of a second after the Big Bang, the universe expanded exponentially fast, far faster than the speed of light, which doesn't violate relativity because it was space itself expanding. This rapid expansion smoothed and flattened the universe, explaining why the cosmos looks so uniform today. But inflation theory also predicts that this process might not have stopped everywhere at once. Some regions of space might have stopped inflating, forming bubble universes like ours, while inflation continued elsewhere, endlessly creating new bubbles. Each bubble would become its own self-contained universe, with potentially different laws of physics emerging as inflation ended in unique ways. In this view, our universe is one bubble in an eternal foam of universes, a single drop in an infinite cosmic sea. New universes are constantly forming, each disconnected from the others by vast expanses of inflating space. We could never travel between them, nor even detect them directly, because the space between bubbles expands faster than light can cross it. They exist beyond any conceivable observational horizon. There's also the quantum multiverse, which arises from the strange nature of quantum mechanics. In the quantum world, particles exist in multiple states at once until observed, a concept known as superposition. Some interpretations of quantum physics, such as the many worlds interpretation, propose that every possible outcome of every quantum event actually occurs, but in separate branching universes. When you make a choice, when a particle decays one way or another, when light takes one path instead of another, the universe splits, creating new realities for each possibility. In this interpretation, there's a nearly infinite number of parallel universes constantly branching off from one another, forming a vast, ever-growing multiverse of all possible histories. It's a radical but mathematically consistent view of reality. Another source of the multiverse idea comes from string theory, a theoretical framework that attempts to unify all forces and particles by describing them as tiny vibrating strings of energy. String theory predicts the existence of extra dimensions beyond the three of space and one of time that we experience. But these dimensions can be compactified or curled up in countless ways, each producing a different set of physical laws. Some versions of the theory suggest that every possible configuration of these dimensions could correspond to a different universe, leading to what's called the string landscape, a hypothetical multiverse of up to 10 to the power of 500 possible universes, each with its own physical constants and structures. These ideas, though breathtaking, raise deep philosophical and scientific questions. If there really are countless other universes, can we ever prove their existence? If we can't observe them, do they belong to the realm of science or philosophy? For many cosmologists, the multiverse remains a useful framework for thinking about why our universe has the properties it does. For example, the anthropic principle suggests that we live in this particular universe not because it's special, but because it's one of the few universes capable of supporting life. If other universes exist with different laws, where atoms can't form or stars never ignite, then naturally we wouldn't be there to observe them. In that sense, our universe might simply be one among many, but the only one we could ever experience. Still, others urge caution. Without direct evidence, the multiverse risks stepping beyond the boundaries of testable science. It's a powerful idea, but one that sits on the edge between cosmology and metaphysics. It could be that the multiverse is real, or it could be that our universe is all there is, a solitary bubble in a cosmic void. Until we find a way to detect signatures of other universes, perhaps through subtle imprints in the cosmic microwave background or gravitational waves that escaped from bubble collisions, it remains speculation, fascinating but unconfirmed. What's undeniable, though, is the profound shift this idea brings to our sense of scale. It expands our perspective beyond even the vastness of the observable universe. It asks us to imagine that what we call everything might be just one small piece of an unimaginably larger reality. For a species that once thought Earth was the center of all existence, that's an extraordinary leap in perspective. And yet, even if our universe is just one bubble among many, there might still be clues within it that reveal its true structure and geometry. The shape of space, the way light travels, and the possibility that the universe wraps around on itself could all hold subtle signatures of something greater. This brings us to an even more mysterious and mathematical frontier: cosmic topology, the study of the universe's hidden shape and how it might be connected in ways we've only begun to imagine. If you could take off in a spaceship and travel in one direction forever, would you eventually reach the edge of the universe? Or would you find yourself right back where you started? This question lies at the heart of one of the most fascinating and mathematically elegant fields in modern cosmology: cosmic topology, the study of the universe's global shape and how space might be connected to itself in complex, almost mind-bending ways. We often talk about the universe as flat or curved, but geometry alone doesn't tell the whole story. Even a perfectly flat universe can have a topology, a way of connecting space that makes it finite or looping. Think of a video game world, for instance. When your character walks off the right edge of the screen, they reappear on the left side. The game's world seems endless, but it's actually finite and wrapped in both directions. That's a simple example of a torus topology, a shape like a donut, where moving far enough in one direction brings you back from the other. Cosmic topology asks whether the actual universe could work in a similar way, but in 3 dimensions rather than 2. If the universe were wrapped around itself like a multi-dimensional torus or sphere, then traveling in a straight line could, in theory, lead you back to your starting point, just like an airplane flying straight around the Earth eventually returns to the same spot, without ever encountering an edge. This idea sounds wild, but it's mathematically possible. Einstein's equations of general relativity don't forbid such a universe. In fact, they allow for countless topological configurations of space. The cosmos could be flat, but multiply connected, curved inward like a hypersphere, or shaped in ways that defy direct visualization. For example, a 3-dimensional space that folds and loops through higher dimensions. From inside such a universe, you'd never see an edge or outside, only the illusion of an infinite expanse, because the space would seamlessly wrap back onto itself. If that's true, then in principle, light could take a similar path. Photons traveling through a multiply connected universe might circle around and re-enter our region of space from another direction, creating ghost images of distant galaxies, or even of our own Milky Way, arriving billions of years later from the opposite side of the sky. In other words, the universe could contain optical echoes of itself, cosmic déjà vu on a universal scale. So, have we found any evidence for this looping, interconnected cosmos? Not yet, but scientists have looked and they continue to search. One of the best places to hunt for clues is in the cosmic microwave background, CMB, the faint afterglow of the Big Bang that fills the entire sky. If the universe were wrapped around on itself, light from the early universe could have taken multiple paths to reach us, producing matching patterns or circles in the sky in the CMB's temperature map. These patterns would be like fingerprints of a finite, looping cosmos. For years, cosmologists have scanned the CMB data, especially from NASA's WMAP and the European Space Agency's Planck satellite, looking for those repeating signatures. So far, no conclusive evidence has emerged. The data suggests that if the universe does loop back on itself, the scale of that loop must be much larger than the observable universe, perhaps so large that we could never detect its repetition from within our limited cosmic horizon. That means we might be living inside a vast, self-repeating structure, but we only see a small section of it, too small to notice the pattern. Still, the search continues. Some recent studies have proposed subtle anomalies in the CMB, tiny temperature variations and asymmetries that could hint at a non-trivial topology. Others suggest that advanced galaxy surveys might someday detect repeating patterns in the large-scale distribution of galaxies, if the universe is indeed finite and connected in a complex way. But these signals would be faint, delicate, and easily lost in the noise of cosmic expansion. Detecting them would require a level of precision and data we've only begun to achieve. Beyond the mathematics and data, cosmic topology invites us to think about reality in a profoundly new way. It challenges the intuition that space must stretch endlessly in all directions or have some sort of outer edge. Instead, it suggests a self-contained geometry where every direction leads back to itself, where boundaries are illusions created by perspective. If you could fly straight ahead forever, you might eventually return to your starting point, not because space curves back, but because space is connected to itself. It's an idea that turns infinity inside out. A topologically wrapped universe could feel infinite even though it's finite, just like how the surface of a sphere feels unending to someone walking across it. You'd never perceive the loop directly because the distances involved would be so immense that no beam of light, no traveler, could ever complete the journey within the lifetime of the universe. And yet, the mathematics allows for it. A cosmos that's whole, connected, and without any outside at all. Of course, until we find hard evidence, cosmic topology remains speculative. But what makes it fascinating is that it's not just an imaginative theory, it's a testable one. The patterns of light in the cosmic background, the symmetry of galaxy clusters, and the subtle correlations in the structure of space itself could one day reveal whether our universe loops in on itself or stretches endlessly. For now, all signs point to a universe that, as far as we can see, behaves as if it's infinite and unbounded. But as we've learned over and over in science, appearances can deceive. We might be cosmic explorers, trapped in a small part of a grander, looping design, seeing only the local patch of a universe that folds in ways our minds can barely conceive. Still, whether the universe loops or stretches forever, we can only measure so much of it. Our ability to understand its true size, shape, and structure depends entirely on what we can observe, and that's limited by light, time, and the reach of our instruments. To know what the universe truly is, we must first face what it is we can actually measure. Despite the universe's staggering immensity, and despite the tantalizing possibilities of hidden curvature, looping geometries, or even other universes beyond our own, we humans have managed to measure astonishing amounts of it. From our small corner of cosmic existence, armed with nothing but light, mathematics, and imagination. What we can actually measure tells us more about the structure, shape, and evolution of the universe than any civilization in history has ever dreamed possible. Yet, it's also a humbling reminder of how little we still know. Let's begin with the single most important measurement ever taken in cosmology, the cosmic microwave background, or CMB. This faint afterglow is the oldest light in the universe, a relic from when the cosmos was just 380,000 years old. Before that time, the universe was too hot and dense for light to travel freely, a blinding fog of particles and radiation. As it cooled, atoms formed, and light finally broke free, streaming through the universe. Over billions of years, that ancient light stretched and cooled as space expanded, until it reached us as a whisper of microwaves detectable with sensitive instruments. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, the CMB is now studied with incredible precision by satellites like COBE, WMAP, and Planck. These observatories have mapped the entire sky in microwaves, revealing an almost perfectly uniform background, but with tiny temperature fluctuations, variations of only a few millionths of a degree. These subtle ripples are gold mines of information. They're the fossilized imprints of sound waves moving through the primordial plasma of the early universe, seeds that would later grow into galaxies, clusters, and the vast cosmic web we see today. By studying the pattern, size, and distribution of these fluctuations, cosmologists can infer the geometry of the universe. If the universe were curved like a sphere, those ripples would appear slightly larger in the sky. If it were negatively curved, like a saddle, they'd appear smaller. But in a flat universe, they match the size predicted by simple Euclidean geometry, and that's exactly what we see. Measurements from the Planck satellite show that the largest fluctuations in the CMB are consistent with a flat universe, to an accuracy of better than 0.4%. In other words, across billions of light-years, space appears geometrically flat, at least within our observable region. But the CMB doesn't just tell us about shape, it tells us about composition. By analyzing its detailed structure, scientists have determined the exact proportions of the universe's ingredients, roughly 68% dark energy, 27% dark matter, and only about 5% normal matter, the stuff that makes up stars, planets, and us. This extraordinary precision gives us a window into the entire evolution of the cosmos, from its first moments to its accelerating expansion today. Beyond the CMB, another way we measure the universe is by mapping the distribution of galaxies across cosmic space. With massive surveys like the Sloan Digital Sky Survey, SDSS, and Dark Energy Survey, DES, astronomers have charted the positions of millions of galaxies, forming a kind of three-dimensional map of the cosmos. When plotted out, galaxies don't appear randomly scattered. They cluster together in long filaments and walls surrounding enormous empty regions called cosmic voids. This structure, often called the cosmic web, is another fingerprint of the universe's underlying geometry and its evolution. The way galaxies cluster and move tells us how gravity has shaped the universe over time. The scale and pattern of these clusters can reveal how fast the universe is expanding and how its curvature behaves. For instance, if space were strongly curved, light from distant galaxies would bend and distort in measurable ways, like a lens warping an image. But we don't see large-scale distortions of that kind, reinforcing the conclusion that our universe is incredibly flat, at least within the region we can observe. Another crucial tool comes from gravitational lensing, where massive objects like galaxies or clusters bend the light of more distant sources. By measuring how light is warped as it travels through space, we can map the invisible matter, dark matter, that makes up most of the universe's mass. This, in turn, helps refine our understanding of how space curves around mass, and whether that curvature is consistent with general relativity's predictions on cosmic scales. So far, every major survey confirms Einstein's model with astonishing precision. We can also measure the rate of expansion, the Hubble constant, which tells us how quickly galaxies are receding from each other due to cosmic expansion. Astronomers use several independent methods to measure this, observing distant supernovae as standard candles, mapping the patterns of sound waves frozen in the distribution of galaxies called baryon acoustic oscillations, and studying the CMB itself. Each technique gives a slightly different value, leading to one of the great puzzles of modern cosmology, a subtle but persistent disagreement known as the Hubble tension. Whether this discrepancy hints at new physics or just reflects measurement errors remains one of the most hotly debated questions in science today. Together, these measurements, from the CMB, galaxy surveys, gravitational lensing, and supernovae, form the foundation of what's called the Lambda cold dark matter model, the most successful and widely accepted description of the universe. According to this model, the universe began with the Big Bang about 13.8 billion years ago, has been expanding ever since, and is dominated by dark energy, which drives its acceleration. Space is flat on large scales, but that doesn't mean it's infinite. It could still be slightly curved, or even loop back on itself in ways too vast for us to detect. So, in summary, what can we actually measure? We can map the relic light of the Big Bang. We can track the clustering of galaxies across billions of light years. We can observe how gravity bends light and shapes the universe's web-like structure. We can calculate the rate at which the cosmos expands. From these clues, we can infer its shape, size, and fate, not through direct exploration, but through the delicate fingerprints left in light itself. And yet, these measurements, for all their brilliance, illuminate only the observable universe, the sphere of reality whose light has reached us. Beyond that horizon lies a realm we can never measure, where the laws of geometry and expansion may take forms we can only imagine. Even if we had perfect instruments, even if we could observe forever, the finite age of the universe and the finite speed of light mean there will always be limits to what we can know. And that leads us directly into one of the most fascinating and misunderstood concepts in all of science: infinity. What does it really mean when cosmologists say the universe might be infinite? Does infinity mean endless stars, endless galaxies, endless versions of everything? Or does it mean something far more abstract, a mathematical idea, not a physical reality? When scientists say the universe might be infinite, they're not necessarily suggesting that there are endless galaxies, stars, or planets stretching into the distance forever, filling every corner of space. Instead, they mean something more subtle and much harder for the human mind to grasp. In cosmology, infinity doesn't describe an observable quantity or a place we can reach. It's a mathematical concept, a model that describes space as having no limits, no boundaries, and no edge where it stops. To understand what scientists mean by an infinite universe, let's first separate the idea of physical infinity from mathematical infinity. In mathematics, infinity is not a number or a measurement. It's a concept. It's what we use when something has no endpoint. The number line, for example, is infinite. No matter how high you count, there's always a number beyond. You can keep going forever. Similarly, an infinite universe is one where space itself never ends. No matter how far you travel in any direction, there's always more space ahead of you. But that doesn't mean there are infinite objects filling it. Most of that infinite space could be, and likely is, completely empty. In cosmology, when we describe the universe as flat, that flatness implies that, unless it's wrapped in some hidden topology, it could be infinite in extent. Parallel lines never converge, they continue forever. The equations of general relativity allow for such a universe. one that stretches without bound, uniform in all directions, with no center and no edge. If you could freeze cosmic expansion and travel infinitely fast, you'd never find a wall, a border, or an outside. You'd just keep going, forever. But here's the catch. We'll never be able to prove that the universe is infinite. Why? Because we can only observe a finite region. The observable universe, a bubble about 93 billion light-years across, limited by the age of the cosmos and the speed of light. Beyond that bubble, we simply can't see. Light from farther regions hasn't had time to reach us yet, and because of the accelerating expansion of space, much of it never will. So when cosmologists talk about the universe being infinite, what they're really saying is, our best measurements show no sign of curvature or edge within the part we can see. And the simplest explanation consistent with that is that space goes on forever. It's a model, not a proven fact. The possibility of infinity in space raises some astonishing and unsettling implications. If the universe is truly infinite, and the laws of physics are the same everywhere, then every possible arrangement of matter must occur somewhere, simply because infinite space allows infinite possibilities. Somewhere out there, unimaginably far away, there could be another galaxy identical to the Milky Way, another planet identical to Earth, another version of you reading these very words, living a life that mirrors yours in every detail, except maybe for one small difference. Not because of magic, but because in an infinite expanse, even the rarest configurations will repeat an infinite number of times. This idea, the infinite repetition of patterns in an infinite universe, isn't just science fiction. It's a direct mathematical consequence of infinity itself. If the universe contains a finite number of possible particle arrangements within any region of space, and if space goes on forever, then those configurations must recur. Somewhere, far beyond the reach of any telescope, might be an exact copy of our entire observable universe, a cosmic doppelganger floating trillions upon trillions of light-years away. And there would be infinitely many more beyond that. Of course, these ideas are speculative. Infinity is not something we can test or observe. In fact, many physicists are cautious about treating infinity as a literal physical reality. Infinities appear in physics equations all the time, usually as signs that our models have reached their limits. For instance, when we talk about singularities at the center of black holes or the Big Bang, those infinite densities and temperatures are signals that our equations break down, not that such physical infinities actually exist. Likewise, an infinite universe could be an approximation, a mathematical ideal that works well for describing what we can see, but which might not reflect the true finite structure of the cosmos. It's entirely possible that the universe is so large that for all practical purposes, it behaves as if it were infinite, even if it's technically finite and loops back on itself in some incomprehensibly vast topology. In other words, it could be functionally infinite from our perspective. To us, it would make no difference, because the limits, if they exist, are too far away to ever detect. Whether the universe is truly infinite or just indistinguishably large, we'd experience it the same way. Infinity also poses deep philosophical questions. Can something truly infinite exist in nature? Does infinity have physical meaning, or is it just a tool our mathematics uses to describe the limitless? Humans struggle to comprehend infinity because our experiences are bounded. Everything we've ever known has a beginning and an end. We can imagine very large, but not without limit. The idea that space might continue forever, that existence itself has no edge, defies the brain's sense of scale and boundary. Yet the evidence so far leans toward that conclusion, at least within our horizon. The cosmic microwave background appears flat. The large-scale structure of galaxies shows no curvature. Light from the farthest reaches of space travels in straight lines, not bending around a closed geometry. These clues all point to a universe that behaves as if it's infinite. Whether it truly is, or whether it wraps around in ways too subtle to detect, remains one of the greatest unanswered questions in all of science. But even if the universe is infinite, we will never see all of it. The finite speed of light and the ongoing expansion of space impose an unbreakable barrier on what we can observe. No matter how advanced our instruments become, we'll always be confined within our own observable bubble. The regions beyond will forever remain hidden, beyond light, beyond reach, beyond knowledge itself. And that realization leads to one of the most humbling truths in cosmology. Even in an infinite universe, our vision is finite. We can only ever know a limited part of the cosmos, and the rest will remain forever beyond the horizon of discovery. That horizon isn't just a physical boundary, it's the ultimate reminder of our place in the grand cosmic story. But what exactly defines that limit of sight and knowledge? Why, no matter how far we look, will there always be regions we can never see? To answer that, we have to return to the fundamental nature of time, light, and cosmic expansion, and confront the unavoidable truth about the limits of human observation. No matter how powerful our telescopes become, or how far technology takes us, there will always be a cosmic curtain we can never pull back, a boundary to what we can see, measure, or even imagine with certainty. This is the limit of human observation, and it isn't a problem we can solve with better tools or more data. It's a built-in feature of reality itself. Because light travels at a finite speed, and because the universe has a finite age, there's an ultimate horizon beyond which we can never look, a cosmic boundary written into the fabric of space-time. Every time you look up at the stars, you're peering into the past. The light from the moon takes just over a second to reach you. The light from the sun is more than 8 minutes old. When you gaze at the nearest star, Proxima Centauri, you're seeing it as it was over 4 years ago. The Andromeda Galaxy? You're looking at light that began its journey 2.5 million years ago, when early humans were still shaping stone tools. Push this further, and the most distant galaxies we can see appear as they were over 13 billion years ago, when the universe was young and the first stars were forming. Every image we capture from deep space is a kind of time capsule, a fossilized moment preserved in light. But there's a limit to how far back we can look. Because the universe is about 13.8 billion years old, light hasn't had infinite time to reach us. Even though space itself has expanded, carrying galaxies much farther away since that light was emitted, the simple truth is that there's a maximum distance from which any light could have possibly arrived since the beginning of time. That distance defines the observable universe, a sphere around us with a radius of about 46 billion light-years. It marks the boundary between what we can see and what we cannot. Beyond it, the light from galaxies and stars hasn't had time to get here yet. And because the universe keeps expanding, some of it never will. This cosmic horizon isn't a physical wall. It's not made of matter, energy, or any kind of barrier you could fly a spaceship into. It's simply the limit imposed by time and the speed of light. The laws of physics set that limit, and no technology can overcome it. Even if you could travel at the speed of light, which you can't, you'd still never reach or see beyond it, because the universe is expanding faster than you could ever move. The galaxies near the edge of our observable universe are receding from us at nearly the speed of light, and those beyond it are receding faster than light, not because they're moving through space, but because space itself is stretching. That means there are regions of the universe, vast, unimaginable regions, that are forever disconnected from us. Their light will never reach us. Their existence, while almost certain, will remain forever hidden. No matter how long we wait, or how advanced our civilizations become, there are parts of the cosmos we will never see, never touch, never even confirm. In those unreachable realms, galaxies form, stars are born, and worlds might exist. But to us, they might as well not. They're beyond the horizon of knowledge. This limitation is sometimes called the cosmic event horizon, and it's not just a physical boundary, it's an epistemological one. It marks the edge of the knowable universe, the dividing line between the visible and the eternally invisible. Just as we can never see inside a black hole's event horizon because light can't escape it, we can never see beyond our universe's horizon because light from those regions can't reach us. The difference is that our horizon isn't shrinking, it's expanding with time, carrying more and more of the universe beyond our reach with every passing second. Even now, as we speak, entire galaxies are slipping away into the darkness, their light stretched and diluted by the accelerating expansion of space. Billions of years from now, the universe we can observe will contain far fewer galaxies than it does today. Eventually, all galaxies beyond our local cluster, the Milky Way, Andromeda, and a few smaller companions, will fade entirely from view. Future observers, living trillions of years from now, will see nothing but a lonely island of stars surrounded by infinite darkness. To them, the cosmos will appear static and empty, and the evidence of an expanding universe, the redshift of distant galaxies, the afterglow of the Big Bang, will be gone. They'll never know the vastness we can see today. This is one of the most haunting truths of modern cosmology. We live at a privileged moment in cosmic history. We can still see the faint echo of the Big Bang, still map the structure of galaxies across billions of light years, still witness the universe in its youthful glow. But this window of cosmic awareness is temporary. The deeper the universe expands, the more of it will slip beyond the boundaries of the observable. Our cosmic horizon grows, but what it reveals shrinks because expansion outpaces light itself. And so, the ultimate question, does space end, may forever remain unanswered. Even if the universe has an edge, or wraps back on itself, or contains other regions vastly different from our own, we may never know. Our cosmic horizon ensures that there will always be mysteries beyond our reach, realities that exist but are forever beyond observation. The universe could be finite, infinite, or part of something far greater. But from our vantage point, we're trapped inside a bubble of light, watching only a small portion of the grand show. This realization can feel frustrating, that our view is forever incomplete, our knowledge forever bounded. But it can also be deeply humbling. It reminds us that, despite our intelligence and technology, we are still tiny beings perched on a small planet, looking out through a narrow window into the infinite unknown. What we see is magnificent, but it is not the whole story. There will always be more, perhaps infinitely more, hidden beyond the light. And yet, in that realization lies something profoundly beautiful. Because while we may never observe the ultimate edge of space, the very act of asking, of wondering, connects us to the vastness we cannot see. It's in our nature to reach beyond horizons, to question what lies beyond what we know. That impulse, curiosity, is the light that no cosmic expansion can dim. It leads us, inevitably, to one final reflection. Perhaps the question, does space end, is not just scientific, but philosophical. Perhaps it's not the universe's boundaries we seek to understand, but our own. At this point, the scientific discussion begins to melt into something deeper, something almost spiritual. We've traveled from the measurable to the unknowable, from galaxies and geometry to the limits of light and time. And now, inevitably, we come face to face with a question that science alone can't fully answer. Does the idea of an end even make sense when we talk about space? Or is the end just a human concept, a product of minds that evolved in a world where everything does end, trying to wrap itself around an infinite reality? From the very beginning of our species' story, we've defined existence through boundaries. The horizon marks where the sky meets the sea. The forest ends where the plains begin. Every path we walk has a destination. Every life we live has a start and a finish. To us, limits are natural. They give shape to experience, structure to thought, and meaning to time. So when we lift our eyes to the cosmos and ask, where does it end? We're really projecting that same instinct onto the universe itself. We're trying to draw the same kind of boundary that exists everywhere in our everyday world. But the universe, vast, timeless, and self-contained, doesn't play by the same rules. Perhaps the question itself is flawed, a linguistic trap. To ask, where does space end, assumes that space exists in something, that it's expanding into somewhere, or that there's an outside to point to. But as we've seen, space isn't contained within anything. It's the stage on which everything else exists. The very fabric of where asking where space ends is like asking what lies north of the North Pole, or what color is beyond the edge of the rainbow. The question collapses under its own assumptions. The universe might not have an end, not because it's infinite in the way we picture infinity, but because end doesn't apply. This realization is both unsettling and liberating. It reveals how our human need for edges, borders, and closure may be a kind of cognitive illusion, a habit of perception that doesn't extend to the scale of the cosmos. We are finite beings, evolved to navigate finite environments. Our brains are wired to measure, to categorize, to draw lines between things. But space defies that instinct. The universe is not a thing sitting somewhere else. It's all there is. Beyond it, there is no beyond. The notion of an edge of everything is paradoxical, a contradiction dressed up as a question. And yet, that paradox is beautiful. It shows how far our curiosity can reach, how our minds can press against the very limits of thought. When you stand beneath a dark sky, looking out at the stars, you're not just staring at distant suns. You're staring at the edge of knowledge itself. The light you see has traveled across billions of years to reach you. Some of it left its source before the Earth even formed, before life began, before the human mind existed to wonder about it. That light carries not just information about the cosmos, it carries a silent message about our place within it, that we are conscious fragments of a universe trying to understand itself. In that sense, the question, does space end, becomes more than a scientific curiosity. It becomes a mirror held up to the human condition. We seek boundaries because they comfort us. They make the infinite feel understandable, containable. But maybe the true lesson of the universe is that not everything can be contained. Maybe the cosmos invites us to let go of the idea of an edge, and instead accept that we live within something boundless, not necessarily infinite in the mathematical sense, but infinite in its depth, mystery, and possibility. Think about this. If space has no end, then everything, all of existence, is connected. Every atom, every galaxy, every beam of light shares the same cosmic fabric. There's no outside, no separation, no other side. The universe isn't a collection of isolated parts, but one continuous whole, stretching through dimensions and time beyond our comprehension. And we, made of the same atoms forged in ancient stars, are part of that whole, not observers of the universe, but expressions of it. So perhaps the real question isn't whether space ends, but whether our way of thinking about endings is big enough to contain the truth. Maybe space doesn't end because it doesn't need to, because the universe isn't something that exists somewhere, but the very framework that defines what somewhere means. Maybe the universe has no boundaries, not because it's endless, but because boundaries themselves are illusions born of limited perspective. From this viewpoint, to ask if space ends is to ask if understanding can ever end. And the answer to that, perhaps, is no. As long as there are minds to ask the question, to stare upward and wonder, the search itself continues. The act of questioning becomes infinite. And that's the most human thing of all. Because even if space has no edge, curiosity does not either. Whether space ends or not, perhaps the most astonishing truth is that we, fragile, fleeting beings on a tiny blue world orbiting an ordinary star, are even capable of asking the question. Think about that for a moment. For nearly all of the universe's 13.8 billion years, there was no consciousness to wonder, no eyes to see, no mind to ask, does space end? Yet here we are, made of the same atoms born in ancient stars, contemplating the structure of everything that exists. Our species emerged only yesterday on the cosmic calendar, and yet we've already stretched our vision across billions of light years. We've mapped the cosmic microwave background, the faint afterglow of creation itself, and traced the geometry of space. We've peered into the birthplaces of galaxies and reached back to the first moments after the Big Bang. We've learned that time and space are woven together, that light has limits, and that our view of the universe is both vast and small at once. And still, our curiosity refuses to stop at the horizon. We push further. We imagine universes beyond our own, speculate about dimensions we cannot perceive, and dare to describe the infinite in the language of mathematics. We build machines, telescopes, detectors, satellites that extend our senses into realms our bodies could never reach. Each discovery opens another layer of mystery, another question more profound than the last. In that sense, science isn't about reaching answers. It's about widening the circle of wonder. The question, does space end, is not just a scientific inquiry. It's a reflection of the human spirit. It captures what it means to be conscious in a universe that may have no boundaries, to feel the pull of the unknown and the ache to understand it. Whether space is infinite, finite, flat, curved, looping, or endlessly expanding, the deeper truth is that we are participants in it. We don't merely live in the universe, we are the universe, briefly aware of itself. Consider how extraordinary that is. From atoms born in the cores of dying stars, consciousness arose, fragile but luminous, capable of questioning the nature of infinity. The universe has spent billions of years unfolding into galaxies and stars and worlds, and on one of those worlds, life evolved into minds that could look back at the cosmos and wonder where it ends. It's as if the universe built within itself the capacity to gaze into its own depths and ask, what am I? And perhaps that's the real answer. Maybe the point isn't whether space has an edge, or loops back, or stretches forever. Maybe what matters is that we're here, able to ask, to imagine, to explore. Every time you look up at the night sky, you're not just seeing stars scattered across a black canvas. You're seeing the story of creation, written in light, a story that began long before you, but that you, somehow, have become a part of. In the end, space might have no boundaries, but our wonder certainly doesn't either. It stretches across time, across generations, across the distances between stars. It's the same wonder that drove our ancestors to light fires beneath the stars, to build observatories on mountaintops, to launch telescopes into orbit, and to send robotic emissaries beyond the edge of our solar system. It's the same force that drives a child to look up and ask, what's out there? And maybe that question, that simple, timeless act of curiosity, is the greatest legacy we'll ever leave behind. Because no matter how small we are, no matter how little of the universe we'll ever see, our ability to ask gives meaning to the vastness that surrounds us. It bridges the infinite and the finite, turning emptiness into wonder. So whether space ends or not may ultimately be less important than the fact that we have the imagination to ask it. From a small planet orbiting an average star, somewhere in the spiral arm of a galaxy among billions, we've dared to stretch our thoughts to the edges of everything, to ponder eternity, infinity, and the mystery of existence itself. And that, in itself, is cosmic. That's the universe dreaming through us, tiny sparks of awareness reaching for the infinite. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.